Till now we have seen an example where the two classes are perfectly separable. What if there is some noise in the data? What if the points are not that easily separable? Like, forget about linear separation. If there is some noise where we need to fit a like totally non-linear curve that will separate these two classes, or that will be used in classification. What if the overall data can be perfectly classified, but except few points where it's almost like noise, they are totally against the overall trend. Now, how to find a hyperplane that will perfectly fit to this data? So this is the hyperplane. Generally we say that that will separate from this class from this class, but whereas now there is this noise in this data. If we really have to and consider this noise, then we might have to fit something like this, where everything above this is positive, everything below this is negative. Is there a better way to do this? So it can be solved by allowing something called slack variable. So there are some points that are kind of noise, so we should not fit a model for the noise. That will lead to overfitting. To have a model that can be very well generalized, we need to ignore the noise points. So that means we need to fit a model that might not 100% classify positives from negative. We can allow some error. So let this be the hyperplane, even knowing that this is wrongly classifying this as negative. Let this be the hyperplane, even though we know that this is wrongly classifying this point. So that is called allowing a slack variable in the hyperplane. So while calculating the hyperplane, we allow a slack variable, and we see that instead of having the point here, we are having the point here that is on the noise. So we don't fit a model that will count the noise. So in fact, it is as simple as we are allowing some error while building the model itself, just to have a robust model, just to have a good generalized model that can work very well on the new data points. So SVM will find the maximum margin classifier, allowing some minimum error due to these noise points. So that is called soft margin classification for noisy data. So SVM will automatically take care of that, so that using slack variables. So we don't need to imagine that all the time these two are perfectly divided as two classes. So SVM validation, how do we do SVM final output, whether it is right or wrong? So SVM doesn't give any probability, as we already observed. It directly gives us the resultant classes, whether it is class 1, class 2, or whatever is the actual class of the data point that we have supplied. Usual methods of validation like sensitivity, specificity, accuracy, ROC curve, AUC, they are all the actual validation methods that can be used. What is the percentage of classified, what is the percentage of misclassified, they and all will apply like any classification problem. Now, what are some of the advantages and disadvantages of SVM? SVM advantages: SVM are like very good when you have no idea on data, like the data set that you are handling. If you have no prior business knowledge and what each variable represents, we have no idea, then we can just start with SVM classification and see how well we can fit the model. SVM works well even if the data is unstructured or semi-structured, even like the data is images, trees, etc. With the kernel trick in place, SVM is a real great model classification algorithm, because we can model any type of non-linear classification problems using the kernel trick very easily. Unlike neural network, SVM doesn't solve for local optima. That means we'll have one unique solution no matter how many times we run SVM, whereas in neural network we might get different solutions depending on the local optima that we get. For high dimensional data, SVM scales pretty well, though it is not really very swift, but at least it is faster than other algorithms like neural network. SVM models have very good generalization in practice, so the overfitting is slightly less in SVM compared to other algorithms. Now there are some disadvantages of SVM. Those are like kernel function, though it is a strength, but choosing the right kernel function is not always easy. And if we have training data, large training data, then we might have, training time might be, or more time taken to build the model might be really high. Now SVM output, the model, it's difficult to understand and interpret the model. Variable weights and individual impact is not very straightforward as other models. So since the final model is not very easy to see, to do some small calibrations and to incorporate some business logic, it's not that easy in SVM. So there's, many applications of SVM. In fact, wherever neural network can be applied, most of the business classes you can apply SVM. So protein structure prediction, image recognition, handwritten digit recognition, breast cancer diagnosis. There are many places where SVM can be applied, where many places where the data is unstructured or semi-structured, where the objective space is highly nonlinear, we can go with SVM. We will use a specific example, digit recognition. So we will take the input as 16 by 16 grayscale images. Then there are two that will make us like 256 pixels will be given as input, and there is one label whether that particular pixel hold together that picture is 1, 2 or 3. So what we'll do is we'll build an SVM model that will recognize the digits finally, like given all these pixels, SVM should automatically predict what digit is it for a new data set, and we'll build a model, then we'll see what is the final accuracy of the model. So let us try to build an SVM model on this digits recognition data, handwritten digit recognition data. This is the training data. Need to change the path. OCR. OCR. Datasets. I'll just change the path of the file, then we can continue the demo. So this is the training data. This works now. And let us see the test data. Let's import test data as well. Now these are the details of the training data. There are 7291 rows, 257 columns, because 256 are the pixels, 7th one is the label. And the test data will have only test data again has 2007 rows and 257 columns, with 256 column being pixels, 257 7th column is final column is label. We can use it for testing. Let us draw some of the images, initial few images in this data set. Let's say initial 6 images we'll draw one by one. These are the initial 6 images. This is label 3, this is label 7, 4, let us adjust it, 4, 5, label is 5. The pixels are adjusted and then finally drawn, so this label is 6. We can see that, like, it's kind of, if we see it, if we rotate it 90 degrees, we can see that it is 6. Let us see if there are any missing values in this data set. There are no missing values at all. Now let us see how many numbers are there in the training data. 0 is coming around 1000 times, 9 has come around 644 times, and then in test data this is the frequency of each of the labels. Now it's simple. We need E1071 library to build an SVM. E1071 has many more functions. We are going to use SVM out of that. I have just attached E1071 library. We will keep an eye on the time. How much time does SVM take? SVM is quite fast, and then we will try to use first 5000 digits. In fact, we will use the complete data set itself for training. So now the SVM has started. SVM model building started. It will try to build a model, and then we'll see the summary. Then we will see what is the accuracy of the model on the training data, and then we can see out of time data validation on the test data. Type is C because it's classification. Variable 1 is label. Remaining all 256 variables are our pixels.